As the last topic in the integration chapter, we'll cover Romberg integration, which is a very nice method of taking simple trapezoidal integration rules and finding a very nice accurate result out of it by taking a series of averaged results. So this ends up looking a lot like the Newton division tree by the time you're done, Newton's dividing polynomials. But you do this with trapezoidal integrations at first. So a couple steps. Step one, you calculate the integral with composite trapezoidal method several times. Namely, you figure out the maximum number of points you are willing to throw into the trapezoidal rule, and then use a smaller subset of those intervals, dividing the interval count by 2 in each step till you get down to something that's rather sparse. So really determine the maximum number you care to calculate first, and then keep dividing the interval count by 2 until you've probably ended up with just a handful of intervals at the base level. Second step, you use Richardson's extrapolation formula, which conveniently is described and developed on the previous page, if you care to go through that, to sequentially improve the estimate of the integration. So you have this entire column of trapezoidal integrals of different accuracies, really. By using different numbers of interior points, you're using larger step sizes as you go back into lower grid resolutions, and then now you start combining them in intelligent ways such that the overall estimate of the integration improves. So successive integration, the second row first element would be 4 times I21 minus I11 divided by 3. So this would be 4 times the second to worst grid count minus the worst grid count divided by 3. And this, as you might expect, really needs a visual guide for how things are combined. So the first column would be all of your trapezoidal integrations in a column, where the bottom has the most subintervals and the top has the least. So whatever you think is the maximum number of points you can handle would be at the bottom, and then every time you can divide that by 2, so going from this, in this case, 32, maybe it's 32 points, or 32 intervals, 16 intervals, 8 intervals, 4 intervals, 2 intervals, and then just 1. That'd be a terrible trapezoidal estimate. But overall, it combines to make an improvement. Maybe you only have 16 intervals, maybe you only have 8. There's no requirement or nothing magic about this size of Romberg integration. It's just this shows you the methodology. What's nice is if you look at this error on the bottom. So the first trapezoidal integration has order h squared of error, then it goes to order h fourth, then order h to the 10th and 12th, and so on and so forth. If you care to continue increasing the number of steps taken to improve your estimate. So you end up following this formula 965 to determine which estimates to add together. So notice here in the first improvement, you would take the integration form, it's called I12, and then the formula for how to generate I12 is given down here in the following formula. So let's actually work through one of those. I could talk about this, but that's not going to do us any good. Let's go to surface writing. So we have, looking straight at equation 965, I of ij. So let's do the 1, 2 point. We actually have that given to us on the previous page, but whatever, let's derive it, make sure we get it right. So I of 1, 2, which is I and j respectively, equals 4 to the j minus 1. So that'd be 4 to the first power times I. This is a previous integral of I plus 1, so it'll be 2, j minus 1, 1, minus I of I, so it carries straight over I of 1, I of j minus 1. So j minus 1 will be 2 minus 1, 1. All divided by 4 to the j minus 1. So again, that'd be 4 to the first minus 1, which we can combine using our high-level math to 3. All right, so I21, if we go back to the textbook to plug things in, would be our second worst trapezoidal method integration minus our worst one, but of course the weighting steps in to help improve things. So 4 times our second worst minus our worst divided by 3 gives us the improved integration method, and that should exactly correspond to equation 961 where we discussed I1, 2. So exactly the same formulation, but this generalized form 965 lets you develop the improvement formula for any given location in this triangle. So of course the best integral is the fifth estimate of order h squared error, and this really can be demonstrated quite nicely in the book's example 9.3. So integrating from 0 to 1 the function 1 over 1 plus x, and they start with, well, conveniently, let's make a note of that. The exact answer, 0.693147, we'll come back to that. They start with 4 different estimates, 4 different numbers of intermediate regions. So even with their best applied trapezoidal method, they get 0.69412, and if reality is 69314, that's still off by, well, quite a bit. But they go through 3 different sequential levels of Romberg till they're left with only one estimate. So if you have 4 initial different scalings of interior regions, then you can have 3 sequential improvements of Romberg. If they went to a 5th, so if they doubled the interior region count and did a better trapezoidal method calculation, then they could actually have a 4th iteration of Romberg and improve the answer further. But look how accurate this is in the end, 0.693147. The real answer is 693,147. Now you're saying, okay, Dr. Hayes, that could be a numeric coincidence, and you're right. Sometimes the stars just align and you get lucky. But notice that this is really 4 trapezoidal calculations. Of course, all of the functional evaluations you need for the previous iterations are taken care of in this most complex version, and then it gets simpler and simpler and simpler. So those 4 coefficients, numbers, integrals, yeah, they're everything in this chart's an integral. Those would be integrals. Are the hardest to come by. The rest of this math is actually pretty cake. That's just equation 965. So this is very computationally unintensive. It's almost just free improvement just through advanced algorithm. Thank you, Mr. Romberg. But anyway, the punchline is that you've done 10 actual calculations, 4 of the composite trapezoidal method, which is where most of the work's done, 6 Romberg integration procedure calcs, which, okay, I mean, they're not very heavy. And if you only wanted to gain the same accuracy by just cranking up the division count in the trapezoidal method, you have to use 276 subintervals. Here, they've done that with how many subintervals? Does it say? Using initial size step of h equals 1 subinterval, so this would be 1, 2, 4, and 8 subintervals. Yeah, so it's 8 compared to 276. It really, really pays off to use Romberg to improve the estimate of trapezoidal integration. That's a very, very good way of taking a small number of points and getting a very accurate integration out of the region.